Hi, in this video, I'm going to go through the Edexcel A-level chemistry paper. This is paper 1 from 2020. This is going to be the second half of this paper. I covered the first half of it in an earlier video. Right, so prop-2-ene 1-ol, an unsaturated alcohol. Okay, and the student planned to use bond enthalpy calculation to bond enthalpy data to calculate a value for the enthalpy of combustion. Okay, when researching the bond enthalpy data, the student claimed it is not necessary to find it for the double bond, as you could just double the value for the single bond. Explain why that is incorrect. Well, it's 2 marks there, so I think what you need to say is you need to explain that the double bond is made up of a sigma bond and the pi bond. And they're not the same strength as each other. The pi bond is a little bit weaker than the sigma bond. And so you can't just do that. I don't think you need to draw the, look at the marks scheme, you don't need to draw the picture of the sigma bond and the pi bond, you just need to say that. Okay, so now we've got to calculate the enthalpy of combustion here using the bond enthalpy data. Okay. So it's usually a good idea to draw out the actual chemicals with the bonds. The displayed formula is very easy to forget some a bond being there or something if you don't do that. So here's the prop-2-enol. Okay, and we have got 4 oxygens. Double bonds between the oxygens. And that's going to form 3 carbon dioxides. And 3 waters. So the way I like to do these is I say I'm going to break up all of the bonds here and make this, so we're going to have gaseous atoms, yeah. So not O2 and so forth, just single gaseous atoms, and then we're going to build them all back up again into the products. The red arrow there. Now this one is going to be, this is breaking bonds, so all these values are going to be, this is endothermic, so all these values are going to be positive. Right, so we're going to have there, we've got 347 for the carbon-carbon single bond. We've got 612, sorry, let's do the, yeah, we've got 612 for the double carbon-carbon double bond. We've got 5 carbon hydrogens. We've got 1 carbon oxygen single, 358, and we've got 1 oxygen hydrogen, 464. So if you add all that lot together, you get 5,000. Oh, and don't forget the oxygens as well. Put in my oxygens there. 4 times what is it? 498 for the oxygen double bonds. Right, that comes to a total of 5838, and that is positive because it's breaking bonds, it's endothermic. Now we make these new bonds, so this is going to be endothermic. There's going to be all negative values. So we're going to have 6 carbon oxygens, double bonds in the carbon dioxide, and we're going to have 6 of the oxygen hydrogens. They're 464. That lot comes to minus 7614. And now we want to find out the delta H of combustion here. So we've just got to add those 2 values together. So we're going to go that one. So that's going to be plus, that's equal to 5 838. And Hess's law, we're going to up that one, sticking with the arrow, so it's going to be minus 7614. If you calculate that, it works out to be minus 1,776 kilojoules per mole. That would be the value of delta H combustion. Okay, now explain in terms of entropy why the combustion of prop to enol is always feasible in the gaseous state. Right, well, I'd do it in terms of delta G. So delta G is equal to delta H minus T delta S. We know that this, and if the reaction is feasible, delta G must be negative. Right, we know that delta H, we just calculated, that's very negative. And we can tell by looking at the products. So you've got your propene 1-ol plus 4 oxygens, and that goes to 3 carbon dioxides and 3 waters, all in the gaseous state. Now you're forming a whole load of gaseous stuff here. You've got more moles on the right hand side of the equation than the left as well, so delta S is certainly going to be positive for that. Okay, so delta S is always positive. So that means that this term here, that's minus T delta S, that's always going to be negative, and this is always negative. So delta G can only be negative at all temperatures, so it's always feasible. If you look at the mark scheme, you don't have to explain why delta S is positive, you just have to say it is positive, but that is the reason why that it is positive. Okay, we've got a different reaction here now, and they give us delta H for making ethanol from carbon dioxide and water and ethene. And not surprisingly, that is quite an endothermic reaction. Right. What it wants us to do is it wants us to calculate delta S total and hence determine whether it's feasible or not under standard conditions. So we need to work out, first of all, we need to work out delta S of the system, and we need to work out delta S of the surroundings, which is equal to minus delta H over the absolute temperature T. Right, so let's work out delta S system first of all. Right, so delta S system, that's equal to the sum of the entropy of the product, minus the sum of the entropy of the reactants. So let's work out this, the entropy of the product. So we're going to have, let's do that up here. We're going to have, right, the ethanol is 160.7. The ethene is 219.5, which is one of them. And we've got 6 oxygens, so it's going to be 6 times 205. Right, if you add that lot up together, you get 1,610.2. Okay, now we're going to work out the reactants. So here we're going to have, right, carbon dioxide, so it's going to be 4 times 213.6, and it's going to be 5 times H2O liquid, 69.9. If you add that lot up, that comes to 1,203.9. Let's put the numbers into this equation then. So we get the products 1610.2 minus that for the reactants is 1203.9. That gives us 406.9. 0.3, and it's positive, plus 406.3. Don't forget that's in joules per mole per Kelvin. Okay, now we're going to work out delta S of these surroundings. Because this is in joules here, we need to convert our delta H here from kilojoules into joules. So we're going to, that's going to be equal to 2 and then times 1,000 and divided by, under standard conditions it says, so we need to have 298 Kelvin. That's the absolute temperature. Don't forget my minus sign there. So delta S of the surroundings is going to be minus 9,000, okay, joules per mole per Kelvin. Okay, so you can see the delta S total is definitely going to be negative here. So the reaction is not going to be feasible. So delta S total is equal to, well, we've got 406.3 positive, and we've got this, add this negative value, 9322. So that's equal to minus 8915 joules per mole per Kelvin. It's very negative. It's not going to be feasible at room temperature. Okay. Right. About equilibrium, ethanoic acid, ethanol, and a catalyst for several days. The equilibrium is the equilibrium constant Kc. Write the expression for the equilibrium constant Kc. Well, Kc is going to be equal to the concentration of the ester. I'll just write ester there to save writing that, all that down. The concentration of water to the power of 1 divided by the concentration of the acid, ethanoic acid, and the concentration of ethanol. Right, and we can see that, I didn't ask, but we can see that there are going to be no units for that, and that's useful because that means we don't need to know the volume or the concentrations, because they're going to cancel out, and that we will need to do that later on, I think. Okay, so the initial amounts of ethanol and ethanoic acid were, okay, I'm going to copy this. I'm going to copy that to equation down. Paste that in there. Right, so what have we got? We have got, right, it gives us the initial amounts of the ethanol and the ethanoic acid. And we know the value of Kc. They told us the value of Kc up here, they said was 0.28, and there's no units there. Now we're going to have to work out the amount of each product at equilibrium. Okay, so right, so what we're going to do is we're going to do start moles. I'm going to do equilibrium moles. Looking if enough used up moles as well. Let's do that, used moles. And then I'm going to do equilibrium concentration. Right, it tells us that we start off with 1.2 moles of each reactant. So we've got 1.2 of that and 1.2 of that. And we haven't got any ester, and we haven't got any water. Right, now let's say we're going to use up X of this. So we're going to use up X of that, and that means we've got to use X of ethanol because they react 1 to 1. We're not using any of those up. So equilibrium, what we've got left over, we've got 1.2 minus X, and we've got 1.2 minus X there. And here we are going to have, we will have formed X moles of ester and X moles of water. Now the equilibrium concentration, they don't tell us the volume, so I'm just going to call that V. But that's not going to be a problem because those V's are going to cancel out because we've got the same number of moles on both sides. I'll put it in anyway. Okay, now put that into our equilibrium expression. Okay, so Kc is going to be equal to the concentration of ester, X over V, multiplied by the concentration of water, X over V, divided by the concentration of acid, 1.2 minus X over V, multiplied by 1.2 minus X over V. All of those V's are all going to cancel out. So we end up with Kc is equal to X squared over 1.2 minus X, and that's also squared, and that's going to help us. Right, the value of Kc, they tell us, is 0.28, so let's put that in. Now, you can see, if we've got this expression here. If you multiplied it out, you'd end up with a quadratic equation, and then you can use a quadratic formula to find out the value of X. And that's fine doing it that way, but there's an easier way of doing it. And if you look, there's a lot of papers where they've done this, and so you don't need to use a quadratic formula. It's a bit of a cheat. It's because you start off with the same moles of both of them. What this is, you can take a square root of both sides here. It's kind of a perfect square. So if we do that, let's take the square root of that. So we're going to end up with square root of 0.28, which is, I'll put the value down. The square root of 0.28 is, well, can I just put that down first? 0.28. Square root of X squared, of course, is X. The square root of 1.2 minus X all squared is 1.2 minus X. Right. I'll do my working out up here. Okay, so the square root of 0.28 is 0.529. Well, that's equal to X over 1.2 minus X. So let's multiply that out. Just a matter of doing a bit of algebra. Equal to X. Multiply that bracket out. We end up getting 0.6349 minus 0.529x is equal to X. So that means we've got 0.6349, take the X onto the other side, is equal to 1.529x. So X is equal to 1.529 over 0.6349, and that is equal to 0.415 moles. So our answer then, we are going to say we have got, well, let's put them in here. 0.4x is 0.415 moles. So we're going to have 0.415 moles of water, 0.415 moles of the ester, 1.2 minus 0.4514 is equal to 0.785. And that's 0.785 as well. So that's the number of moles of ethanoic acid and the moles of ethanol. There are our answers there. Okay, so that method of taking the square root instead of using the quadratic formula has come up quite a few times. B, okay. Another ester can be formed by the reaction gaseous phase reaction, okay, and it wants the two bond angles X and Y. Okay, so let's do Y. Well, Y is, you've got 4 bonding pairs around that carbon. No lone pairs, so it's going to be tetrahedral, so it's going to be 109.5 for that one. Around X, well, you've got the double bond, you just count as a single bond when you when you're working out shapes. So we've essentially got 3 bond pairs and no lone pairs. So that's going to be trigonal planar. So that's going to be 120 degrees. So here is our answer. It is C, isn't it? Okay. The reaction often forms an equilibrium mixture. What would be the units for it for Kp? Well, so Kp is going to be equal to the concentration of the ester, sorry, the partial pressure of the ester, because it's a gas phase reaction, divided by the partial pressure of carbon monoxide and the methanol. Right, so what units are we going to use? It's a multiple choice question. They've given us the only pressure units are atmospheres. So we're going to have atmosphere on the top, and we're going to have atmospheres squared on the bottom. So that simplifies out as 1 over atmosphere. So, and that becomes atmosphere to the -1. So that's D is our answer there. Okay. Describe what effect, if any, increasing the pressure would have on the equilibrium constant Kp. Well, changing pressure will have no effect on the equilibrium constant Kp. The only thing that changes the value of Kp is changing the temperature. Okay, now if you look at the equation there, it's tempting to think, right, this is, if it is forming an equilibrium, right, change that into an equilibrium arrow. You've got 2 moles of gas on the left and 1 on the right. So if you increase the pressure, you would expect the equilibrium position to move that way. That's true, it will, but the Kp value will not change. Only temperature changes it. Right. Now we're on to a longish titration question. Okay, a redox titration. All right. So you've got tablets containing potassium manganate are dissolved in water. Okay, the manufacturers claim that each tablet contains 400 mg of potassium manganate. Okay, so you get 5 tablets, make it up to 100 centimeters cubed. We don't need this till later, actually. We put the manganate in the burette and we titrate it against ethane dioate solution. Okay, and right, and so on. Right, now it's a manganate titration. So what we're doing is we have got our potassium manganate. Change that for purple. Okay, purple, nice purple solution in there. And we've got our ethane dioate in the conical flask. Right, when that comes in, the purple stuff, so this is purple, but the other manganese, all the other species are all colorless here. That's essentially colorless, that. So the purple color disappears until you get to the end point when you get the manganate no longer reacts, so it will become purple. So the color change is colorless to pale purple, because you just want to add 1 drop over. Okay, and that's the your endpoint. You don't need an indicator there. Normal potassium manganate titration. Right, complete the dot cross diagram for the ethane dioate ion. So just like, what is the ethane dioate ion? It looks like you've got double bonds. You've got, okay. Right, so let's do the dot cross diagram for that. Right, so I'll do this carbons as crosses, and I'll do this carbons as like triangles, I think, because we're going to need the dots for the oxygens. So there's a single bond between the 2 carbons. Now we've got a double bond here, so I'm going to have triangle. Okay, the triangles are coming from that carbon on the right, the dots from the oxygen. And this one is only a single bond, so we have a dot from the oxygen and a triangle from the carbon. Right, now we need to complete. All right, so I have completed all of those for that carbon. I've got 4 triangles there. Look, if I just do it in green, 1, 1, 2, 3, 4. So we don't need to worry about any more electrons there. for that one. Let's do the oxygens now. Oxygen in group 6. So I've only drawn 2 dots for this oxygen, so I need to draw 4 more. So we have 2 lone pairs. This carbon down here, well, I need to draw, there's only 1, so I need to draw 5. And that's a negative charge in it, so I've got another electron I'll do in blue, which is doesn't really belong to it, and that's why it's negatively charged. I'm going to do the same on the other side now, but this time I've got crosses instead of dots, so I'm going to have cross, triangle. I'm going to have a cross. Sorry, not cross, dot cross, isn't it? Sorry. This carbon's a crosses, yeah. So dot cross, and then the oxygen has got 2 lone pairs. And this oxygen single bond, 5 more electrons, plus another one with the negative charge. It's taken from somewhere else. Okay, let's do the oxidation number of carbon in the ether dioate ion. So I usually do the sum of the oxidation numbers is equal to the charge on the species. Okay, so the charge on the species is -2. How many carbons have we got? We've got 2 carbons, so they're the unknown, so 2C. We've got 4 oxygens, there was -2, so that's -8. So that means you've got a bit of algebra, 2C is equal to +6. Divide by 2, carbon has got an oxidation number of +3. Okay, give the reason why sulfuric acid is also added to the conical flask. Okay, so just go up here. Right. You've got to put, as well as the ethane dioate ion, you've got to put some sulfuric acid in there. Okay, and the reason for that is, well, we look at the equation here, tidy that up. We've got all of this, you need all of these H+ ions. You need an excess of sulfuric acid in order to provide those for the reaction. Okay, right. Now, this redox reaction could be used in an electrochemical cell, and the half equations are given there. Write a cell diagram for this. Now, we know this one is the one that goes forwards. Yeah, this one goes forwards, isn't it? The manganate gets reduced, and this one goes backwards. The ethane dioate gets oxidized. So that means if that one's going forwards, that must be the most positive value, and that's important because our convention, we usually put the most positive on the right-hand side. So here's our salt bridge. That's how we show the salt bridge. Now I need to do the manganate. Okay, so now the other convention is most positive on the right, and also we put oxidized form next to the salt bridge. The oxidized form is obviously the manganate, so I'm going to have the MnO4 minus and 8H plus. Bracket around that. It's just a comma because they're in the same phase. It's not a line to separate it from the reduced form. The reduced form is Mn2 plus and 4 waters. Because there's no metal, element metal, there's manganese, but it's not the element. We're going to need platinum. We do have a phase change there, so it's a straight line and PT. On the other side, then I'm going to have we're going from this equation here, the oxidized form. So I want 2 carbon dioxides. I'd probably be tempted to put, because they're going to be gaseous, so a phase change there, solid line. And then to put the ethane, that's the oxidized form. The reduced form is the ethane dioate ion. So that goes there in aqueous. And we would need platinum as well there. Okay, the results of the titration are shown here. Right, so we need to work out the titers and determine which are concordant. So subtract the initial from the the final from the initial value from the final, we get there, we get 16.8 for that one, 0, and we get 16.9, 0. Now we have to identify any with the concordant. So they've got to be within 0.1 of each other. And so the only two concordant ones are those. Yeah. And an average of those is going to be 16.85 centimeters cubed. Okay. The equation for the reaction. Okay, so for the manganate and the ether diode ions is shown again here. Use this equation and your mean titer, which was 16.85. I'll write that down, to calculate the mass in one tablet. Okay, right. So let's do that. And I've just pasted the first information, the information for the question there, so we can refer to that. Okay, so we need to work out the moles of ethane dioate first of all. Okay, and we can do that because we know the volume and we know the concentration. So the moles of ethane dioate in the conical flask . That's in the conical flask. Concentration times volume, which is 0.2 multiplied by 25, so that's 0.025 dm cubed. That is equal to 5 times 10 to the minus 3 moles of ethane dioate. Okay, now how many moles of manganate does that react with? So we've got 5 moles of that react with just 2 moles of manganate. So I'm going to write down the moles of MnO2, MnO4 minus, sorry, is going to be the moles of that. We're going to multiply it by 2 over 5. And that gives us 2 times 10 to the minus 3 moles of manganate. Okay. Now this was the moles of manganate in the titer, which was 16.85. Okay, so that's in 16.85 centimeters cubed. So now we're going to work out the concentration of the manganate solution that we've made. So I'm going to do that there, here. So the concentration of the manganate ion solution, moles over the volume. We worked out the moles as 2 times 10 to the minus 3. We've got the titer here, 16.8, so that's in dm cubed, that's 0.1685. Okay, so that works out to be 0.1187. Okay, so we've got a concentration of our manganate there. Now, we made 100 centimeters cubed, so that was the total of that. So we will total moles of manganate. We'll do that now. Okay, so total moles of manganate. Is equal to the concentration multiplied by the volume. So that's 0.1187 multiplied by 0.1. That's 100 centimeters cubed in dm cubed. Yeah. So that is 0.01187 moles. Okay, that's the total moles of manganate. So that's the total moles of potassium manganate. Now the MR of potassium permanganate, 39.1 for potassium, 54.9 for manganese, 4 times 16 for the oxygens. That gives you 158 exactly. Okay. Right. So now we need to work out the mass of the potassium manganate. So mass is equal to moles times MR. the moles is 0.01187 and the MR 158. That is equal to 0.3744 grams. Okay, multiplied by 1,000 because we've got to give it in milligrams. That's 374.4 milligrams. I think we should only give it to 3 significant figures because all our data is to 3 significant figures. So that's 374 milligrams. Is our final answer. Okay. This is the last question on the paper now. Right. A textbook suggested the conical flash should be heated during the titration as the reaction between the manganate ions and the dichromate ions is slow. Okay. Use these electrode potentials and your knowledge of homogeneous catalysts to deduce why heating is very important at the start, but less important as the titration proceeds. Right. So what the overall reaction is, of course, was, I'll just write down the overall reaction. It's going to be 2 manganates plus 16 H pluses plus 5 ethan dioates. And that is going to go to 2 Mn2 plus 10 carbon dioxides and 8 waters. Just so we know the reaction. Now, what this question is about is autocatalysis, of course, and that you should know this, but that this reaction is catalyzed by Mn2 plus ions. So the product of the reaction actually catalyzes the reaction. Right. So at first, the reaction is slow because there's no catalyst here. Right. Now, if you look at the mark scheme, it says the reaction is slow because both manganate and the ethan dioate are both negatively charged. So they're going to repel. And it says that in textbooks and mark schemes, but I don't think it's actually true because you had all this acid here. This is only a weak acid. That's going to be protonated, I would have thought. So that's not going to be negatively charged under those circumstances. But anyway, that's what it says in the mark scheme. Right, so they're both negative, so it's got a high activation energy. So it's a slow reaction. Okay, because they're going to have problem colliding with each other. So if you look at the electrode potential values, we've got to explain why the Mn2 plus acts as an auto catalyst. So let's first of all look at these 2 half equations here. The manganate is the most positive, so that's going to go forwards and it's going to oxidize Mn2 plus to Mn3. Okay, so the manganate is going to oxidize Mn2 plus to Mn3. And now let's look at these 2 equations. Sorry, change color, so I'm in blue. All right, now look at this pair of equations. This time it's the Mn2 plus 3 plus, which is the most positive. So that is going to that is actually going to go that way, and that the Mn3 plus is going to oxidize the ethan ions to CO2. Okay, so these don't need to collide. The manganate don't need to collide with each other because the Mn2 plus will catalyze the reaction, and you need to explain, why. Well, you need to explain, like I did with the 2 green equations, as I did in green there. You need to explain that MnO4 minus will oxidize Mn3 plus because the E value is more positive. And then you need to say that the Mn3 plus will then oxidize the will oxidize the ethane dioate ions because that E is more positive. Okay, so that is the end of the paper.